Okay, so this is going to be an introduction to capacitors. So imagine that you take your power supply that you used in the lab and you connect it by two wires to an apparatus which is just composed of two metal plates that are separated by a small gap. The power supply will pump some charge to the top plate and suck it off the bottom plate. So the top plate ends up being positively charged and the lower plate is negatively charged. Now, if you imagine changing the settings of your potentiometer so that the voltage changed, the amount of charge on the plates would change also. It ends up that that amount of charge is proportional to the voltage that you set the potentiometer to. So if the voltage is really high, there's a lot of charge, and if it's low, there's a little charge. The proportionality constant, the C in this equation, is called the capacitance. Now, of course, we know our relationship here between electric field and the electric potential. So let's use this as an example to practice with of our use of the relationship between the two. So we know that if we take a displacement between any two places, dl, that we can write the difference in electric potential between the initial and final as the dot product between the electric field and the displacement, and then with a minus sign in front of it. So let's practice here. Let's do the case where we take a delta L to go from the bottom plate to the top plate. Okay, in this case, we know the electric field and the dl, the displacement, are in opposite directions, so that their inner product, the dot product, is negative the product of their magnitudes. Okay, the cosine of 180 is -1. The other thing we know is that the difference in potentials, final minus initial, is the supply voltage minus 0. Okay, so the difference is just the supply voltage. Okay, so we know the difference is supply voltage. We know E dot dl is minus EDL. So now if we plug into this general equation, we find that the voltage on the plates is equal to E times D. Okay, it's not so surprising that it works out that way, but all the signs work out perfectly. Yet two minus signs, they cancel, and everything ends up being positive. Okay, so it's just to carefully using the relationship between the electric field and electric potential to make the connection. So let's do the same thing, but this time we're going to switch. We're going to let dl be in the same direction as the electric field. So now the dot product will just be the product of the magnitudes, no minus signs, but the delta V, the change in the potential, Since we've changed initial and finals, we'll switch signs. So now the final is 0 and the initial is the supply voltage. So the difference is minus Vs. So then when we plug into our general equation, we get minus Vs. We have the minus from the equation and a positive ED. Again, the minuses cancel, and we get the same result. Okay, so what we learn here is that you shouldn't worry about the direction of the L, but you should deliberately choose its direction and then work consistently with that. The choice of DL determines whether this is going to be ED or minus ED. It also determines whether it's going to be VS or minus VS. So those signs are not random, and as long as you make clear in your head which is initial and which is final, you can determine those signs clearly. Okay, so a little bit of free education here. I'm going to talk about the charge density on those plates. So again, looking at the plates, we have charge here spread over this whole area there. So that creates a charge density. Okay, so we call the charge density, the surface charge density, the charge per area. Now, it can be shown by using Coulomb's law that in this situation, or actually this is a general result, if you have a surface charge density, that the electric field at that surface is just that surface charge density divided by epsilon naught. That epsilon naught is the same one that's in Coulomb's law. The one where we write K is 1 over 4 pi epsilon naught instead. So this is a really nice result, and we want to use it here. Now the other thing is we also just determined that that voltage divided by D is the electric field. So we can also write the electric field like that. So that means we can take these two expressions of the electric field. We know the electric field is like this now. Put that on that side of the equation. We also know we can write it like that. So we have two ways of writing out the electric field, and that gives us a relationship between something new. So now we do a bit of algebra, solving for the charge on the plates, and we find, sure enough, the charge is proportional to the voltage. And the proportionality constant we know is called the capacitance. Okay, so what we've just found is we've derived in essence what the capacitance is for this parallel plate capacitor. It's really pretty simple. You have the permittivity of free space, the area of the plates, and the distance between the plates. Nice simple result. We're going to want to use that in just a little bit to find something else. So I thought I'd go there. But again, you're not responsible for this derivation. Okay, so now let's talk about energy storage on the capacitor. There's actually current plans for electric cars to use something equivalent to a capacitor instead of a battery. And the advantage of the capacitor for storing energy is that you can charge it and discharge it almost instantaneously. So instead of taking hours to fill up your car with electric energy, you could pull in and fill it up in a couple minutes, just like you do with gasoline. So there's an active area of research. Okay, so let's just think, why is the energy stored? Well, think about it. If it's, you have a capacitor that's charged up here, so you have positive charge on the top plate, negative charge on the bottom plate, it takes work to move some more charge up. So if you want to increase the charge on the top and decrease the charge on the bottom, is going to take some more energy because you have to move that charge across an electric potential, the difference between the electric potential from one plate to the other. Okay, so we know that the amount of energy will be the electric potential times the charge. So I did as a little bit of energy because we got a little bit of charge. Now, the thing is that as you move more charge, the charge on the plate increases, which means the voltage also increases. So using the relationship Q is CV, we can solve for V. Okay, so if you graphed the electric potential versus the charge, it'd be linearly increasing with a slope of 1 over the capacitance. Okay, so again, we can just think the amount of energy for each little added charge. So we just think I'm going to go a little bit more, add a little charge, and now I'm going to increase. And the amount of energy that's added is the height times that dq. It's the width here. We can see that that's roughly this rectangle. Okay, so that's what this is that rectangle. Okay, so that makes it fairly obvious that what we really want for the net is the area under that rectangle, or the area under that line. Or in other words, we need to integrate. So if we charge it up to the total charge to a big Q, we could go through all the little different values of little q, integrating them all together, and you find that we get this nice result here, that the total stored energy is 1/2 1 over c times q squared. If you use the relationship between charge and voltage, we could get rid of one of those q's for a potential, and we have 1/2 q times v, or if we get rid of the other charge as well, we have 1/2 cv squared. All equivalent, 3 different ways to write it. But the important point is, yeah, that we can write the potential energy in terms of the charge or the voltage. Now, I want to use this result up at the top of the page, this guy up here, to rewrite that a little bit. Okay, so the same expression, but I'm going to put in that for the capacitance. So there's the capacitance, and I'm also going to replace the voltage with the electric field times the distance between the plates. Okay, both things that we already showed were true. And then do a bit of algebra. One of the d's cancels, and we get 1/2 epsilon naught a times d e squared. But the area of the plates times the distance between them is the volume of the gap between the two plates. So we can also write it this way in terms of the volume. That means that the energy per volume, or the energy density, is 1/2 epsilon naught times the electric field squared. This actually ends up being where the energy in the capacitor is actually stored. You can think of the space between there, even if it's just air, has some tension in it. Like the electric field, like is a material, the space is like a material being stretched. And there's actually energy in the field itself. Okay? And the amount of energy stored in an electric field per volume is just 1/2 epsilon naught times the electric field squared. It looks a lot like 1/2 mv squared, so it shouldn't be too hard to remember. Okay, so that's an important general result. It works for all electric fields. Any place there's an electric field, there's also energy. Now, one last thing here. It's the idea of a dielectric. So let's go back to our parallel plate. And let's imagine that we fill the gap between with some kind of material that's um, polarizable. Okay, so it doesn't conduct, but it is polarizable, and most materials are polarizable to some extent. Water has a very high ability to be polarized. So just imagine we put something in there. We know that if you put material in an electric field, it's pulling and pushing on the positive and negative charges, so it tends to move them in opposite directions. So what happens is that the net effect is that you end up with a negative charge on one edge, on the top edge here of the material, and a positive charge on the other edge, which creates an electric field, the induced electric field, which is in the opposite direction of the field that was created by the charge on the outside of the plate. In essence, it reduces the electric field strength inside. This means that the electric potential difference from one plate to the other, which is now the net result of the total field, is less. So we'll let V prime be the electric potential difference between the plates with the material in. Okay, so that's the net electric field times the displacement from one plate to the distance from one plate to the other. So that'll be the difference in the fields, which will be less than it was before. Okay, so if remember that was with a fixed charge. I always just had a fixed charge. We didn't change the actual charge on the plates. Okay, so if we think about what's happened to the capacitance, we see that since the electric potential is decreased and the charge is still the same, that means that the capacitance is increased. Okay, so now we have a capacitor that can hold more charge for the same amount of electric potential. This again is handy if you want to store more energy. So it's a very important part of high capacity capacitors. And this is a way of characterizing materials. So you stick them into something like this that creates an electric field, measure the change in the capacitance, and it defines what we call the dielectric constant for the material. Okay, so you have the capacitance with the material is equal to a constant times the capacitance without the material. Okay, and that constant is called the dielectric constant.